Now we're going to start looking at how stars differ from one another. Take a look at this drawing. Try to come up with what is different about how the stars are drawn. What's different about them? The sizes are different. What do you think the different sizes stand for? Turns out this is from a star chart, something that somebody who's looking at the sky could hold up and try to figure out what they're looking at. And so because it's a star chart that you'd look at as you're looking at the stars themselves, the different sizes are actually going to represent different brightnesses that you see in the sky. You can say, oh, the brightest star that I see is Sirius. So when you look at a star chart and you see different sizes, the sizes represent the brightness of a star, how bright you see that star. And the brightest star here is, of course, Sirius, which is the brightest star in our entire night sky. Go ahead and write down today's question of the day. How do we measure a star's brightness, and what characteristics about that star do you need to know in order to do that? First thing that you need to know is what's known as the inverse square law of light. That basically says the farther away you get from something that gives off light, the less bright it seems. Hopefully that's obvious to you. If you are looking at a flashlight that's a mile away, it's not going to appear very bright. Same flashlight held up to your eyeball, it's going to be much brighter. The inverse square law of light is 1 over the distance squared. And again, here is an exponent in the denominator. So if you increase the distance, the brightness is going to drop by a factor of a square. Think of it this way. If you are a distance of 1 away, all of the light that can go through this little box is going to hit that little box. But if you double that distance, that same amount of light is now spread over 2 squared, over 4 little boxes. If you triple the distance, that same amount of light is now going to have to cover 9 of those squares, or 3 squared. So this is going to be much brighter than a box that's just 3 times farther away. This light will appear 9 times brighter if you're standing here versus if you're 3 times farther away. Put another way, if you move back to a distance of 3, it will appear 9 times dimmer. So as you increase the distance from an object, that object is going to appear much dimmer. This was after bell work, and I want to make sure that you guys have read it. This does a much better job of explaining than I just did. All right, the magnitude system. Magnitude is another word for brightness. Whenever you hear the word magnitude, that means brightness. All right. Historically, it was devised by Hipparchus, ancient Greek astronomer, who looked in the sky and said, that star right there is the brightest star that I see, that gets first place. And then the other stars that were not quite as bright got second place. And then the third stars got third place. And he went all the way down to the dimmest stars that he could see, and they got 6th place. Originally, the brightest stars had 1, and the dimmest stars had 6, which means the lower the number, the brighter the star. The higher the number, the dimmer the star. You can't see anything dimmer than a 6, which means if you have a magnitude of 7, that star is, by definition, invisible to our naked eye. Keep this in your head. The lower the number, the brighter the star. The higher the number, the dimmer the star. Time, of course, goes on, and we invent telescopes. And all of a sudden, we can see stars that we've never seen before. We can see stars and objects out there that have never been seen. So that star up there that was a 6, the dimmest we could see, we can now see a bunch of other stars that are even dimmer. So we had to expand from 1, 2, 3, 4, 5, 6, and now we have 7, 8, 9, 10, etc. As soon as we did that, we also decided, well, maybe we need to come up with something so that we could talk about the moon, or we could talk about a supernova. Maybe we could talk about the sun in terms of how bright they are. And in 1856, this guy named Pogson decided that let's make a standardized scale for brightness of objects, a magnitude scale. He came up with the idea that a 6th magnitude, the dimmest thing that you could see with your eye, is 100 times dimmer than a 1st magnitude. Okay? And if you keep going, from 1 to 6 is at 5, so from 6 to 11 11th magnitude would then be 100 times dimmer than a 6th. And if 1 to 6 is 100, 6 to 11 is 100, 1 to 11 is going to be 10,000 times dimmer. He chose the star Vega to be the 0 point. Unfortunately, there are stars out there that are brighter than Vega. So now we have to go lower than 0. We actually have a couple stars that are negative numbers. So 0 is Vega, -1, Sirius, the brightest star in the night sky, is like -1. And then 1, which used to be the brightest, according to Hipparchus, is now no longer the brightest. Here's a question for you guys. Which star is going to seem brighter? A red star with magnitude 1 or a blue star with magnitude 4? Which one has a lower number? The red star does. So the red star is brighter. Which star is hotter? A red star with magnitude 1 or a blue star with magnitude 4? Well, now we don't look at the magnitude, we look at the color, and a blue star is always going to be hotter than a red star. So the blue star is hotter. Which star is bigger? And here we run into a problem. We have no clue, at least not with the information that I've given you so far. This gets into what we call apparent and absolute magnitude. There's two ways to measure the brightness of a star. Apparent magnitude is what we see with our eyeballs. That's how bright it seems to us here on planet Earth. And it depends on two things. One, the luminosity, or how much energy is coming out of the star. And two, how far away it is. That's the apparent magnitude. And it's basically the brightness as we see it here on Earth. These star charts that draw the brighter stars bigger, that is the apparent magnitude, because these star charts are for use here on Earth. And so the stars that we see brighter here on Earth will be drawn bigger. Sirius is the brightest star in our night sky. Its apparent magnitude is the lowest. This guy is looking at two stars, A and B. He sees both A and B the same brightness. However, we can tell that A and B are not giving off the same amount of light. The fact that A is much closer and B is farther away is the reason that we see them being the same brightness. So the apparent brightness, we see them the same. Absolute magnitude is, what if every star was the same distance? Then what would we see as being brighter? So we made up a random distance of 10, because it's a nice round number. If we pretended that every single star was 10 parsecs away, then what would the brightness be? And that is only one variable. Basically, how much energy is coming out of the star. So the absolute brightness is really truly how bright a star is. Apparent brightness is how bright it is to us here on Earth, but if we move them all the same distance away, their apparent brightness would depend on which one's giving off more energy. So the absolute magnitude is how much actual brightness, photons, is coming out of that star. To demonstrate this, we have a number of different vehicles. We have two cars that are exactly the same. Because they're the same, their headlights give off the same amount of light. However, because one of them is parked farther back, the headlights are going to seem a little bit less bright. This is what we would refer to as apparent magnitude. Because from our point of view, even though they're the same brightness, they don't appear the same brightness to our eyes. Conversely, if you have two different vehicles, a truck versus a car, and they are the same distance away, the truck has bigger headlights, and so they are going to appear brighter, not because it's closer, but because it's actually giving out more light. So the absolute magnitude, if you have two different light sources that are the same distance, which one is actually giving off more light? That's going to be the brighter object. That's the absolute magnitude. Apparent magnitude has to take into consideration the distance. Absolute magnitude, which one's actually giving off more light? Another example, star A versus star B. This observer is looking at these two stars. What this observer is seeing is that star A is brighter. So for this observer, the apparent magnitude from their apparent eyeballs looking out into space, star A is going to have a lower magnitude because it's brighter. However, in real life, if you were to go to both stars and measure the amount of energy coming out of them, B has more energy coming out. There's more actual light coming out of B, which means the absolute magnitude would have B being brighter. It would be a lower number. Apparent magnitude takes into consideration distance as well as how much light's coming out. Absolute magnitude just depends on which star is really truly giving off more light. Here's a scale of a couple common objects. We have Sirius, our brightest star, is at -1.5. Alpha Centauri, the closest star to us, is at 0. Polaris, the North Star, is 2.5. The naked eye limit to what we can see is at 6. If you have binoculars, you can see down to a 10. If you look at Hubble, we can see that Hubble is at a magnitude of about 30. The full moon is at -12.5. The sun is at almost -27, which means this is going to be very bright compared to some of the other things in the sky. Which of these stars appears the brightest to our eyeballs? Well, obviously, it's going to be the sun. The sun has the lowest number, but which of these objects is actually putting out the most light? Well, the absolute magnitude tells us that Rigel is putting out the most light. Which of these objects is putting out the least amount of actual light? The object with the absolute magnitude that's the highest is actually the sun. So of all of these stars, the sun is actually putting out the least number of photons. However, because it's so close, it seems the brightest to our eyes. The apparent magnitude does not always match the absolute magnitude. You have to think of the distance involved. We mentioned that the Hubble can see to a magnitude of about 30. James Webb will actually be able to see to a magnitude of about 34. Human sight is at 6, and Sirius is about -1.5. The space station, when it flies overhead, is at -6, so it's brighter than any star in the night sky. Venus is at about -5, also brighter than any star. And now a quick review of everything that I just talked about.
Let's look at another aspect of stargazing basics, this time magnitudes of various objects. Now the word magnitude is just a fancy way to describe the difference in brightness of objects we see in the night sky. And it's not too hard to learn how it works, but let's start with some history. The Greek astronomer Hipparchus developed the magnitude scale back in the 2nd century BC, when he assigned the brightest stars a magnitude of 1 and the dimmest stars that of 6. The in-between stars 2, 3, 4, and 5 magnitude assigned according to their various brightnesses. Using a logarithmic scale, he assumed that the difference in brightness of stars was 2.512 times brighter than the next dimmest one. Taken across that full 6 magnitude scale, that meant that the brightest stars, the first magnitude ones, were 100 times brighter than the dimmest, or the 6th magnitude ones. It also allows for a fairly easy way to determine other brightness differences. The difference from 1st to 3rd magnitude is 6.3 times, 1st to 4th 15.8, 1st to 5th about 40 times. This worked just fine until Galileo turned a telescope towards the heavens and humans discovered there were a lot more stars out there than just the 1st through 6th magnitude ones that they could see naked eye. But what they did was just extrapolate that scale further. So much like golf or ERA in baseball, the lower the number, the brighter the star, and the higher the number, the dimmer the star. 11th magnitude is 100 times dimmer than 6th magnitude, and that 11th magnitude star would also be 10,000 times dimmer than a 1st magnitude star. In the other direction, we have some objects that are brighter than 1st magnitude stars. Hipparchus actually fudged the numbers a bit. The star Sirius in the winter sky is definitely brighter than most other bright stars, and it shines at magnitude -1.4. The planet Jupiter is even brighter than that, often appearing at around magnitude -2, and Venus, brighter still, typically around -4. When objects are bright, they are denoted on star charts with larger dots. Dimmer stars are usually given smaller dots. This helps us locate brighter objects in the sky more easily. But from our perspective, even brighter than the star's magnitudes is that of the moon and sun. The full moon in the night sky shines at magnitude negative 12.7 and the sun at magnitude negative 26.7. Those are both really bright compared to starlight, but also a huge difference even between themselves, as the sun is 400,000 times brighter than the full moon. Now, everything we have discussed has been visual magnitude, meaning how bright or dim objects appear from our location right here on Earth. Now, another concept that you may run across is absolute magnitude, used by astronomers to compare the relative brightness of objects when placed the same distance. But that's a little more complex than what we need to know for simple stargazing purposes. All you need to know about it is that it compares the relative brightness of objects if they were all viewed from the same distance away.
If you guys could go back and answer both questions of the day.